Hello all, welcome to another session for DSP lab. In this session, we'll try to execute a second assignment. So here the assignment is given. So question number 6 here. So you can see that it is asking for multiplexing and demultiplexing of two audio signals of a same sampling rate using DSBSC modulation and demodulation and filters. So here in this assignment we have given with two music signals. First we have to multiplex those two signals, and then later on we have to demultiplex using a proper filter. Okay, so let's start. So here the two signals are given, that you can see that message 1 and message 2. So first we'll try to listen these two sounds, and then later we'll multiplex these two signals, and then we use filters to extract one of the message signal from the multiplexed signal. Okay, so first starting with this one, CLC clear all, close all. Now first reading the first signal and taking that as a M1 with a sampling frequency, and then audio read, message 1 MP4. Okay, we'll try to play this sound first. So I'm stopping this one. Now we'll try to extract the second audio. And giving another variable to this one, and we'll take this as a first sampling frequency and this as a second sampling frequency, and we'll play this sound now. FS2. So this is the second audio, and here you can see that length of M1 and M2 are different, but sampling frequency for the both are same as mentioned in question. So the question mentioned that audio signals have a same sampling rate. Okay, so here we can take as a FS only because both are same. And then here the first thing is that we have to make these two lengths as same. Okay, so we have to truncate one of the signal to make it both as same. So what we have to do, so I'm removing that also. Now you can see that reading audio signal, or you can say this is as a first audio signal, and this is reading second audio signal, right? Now first we will make as take one L and write minimum of length of M1 and length of M2. So this is to know the minimum length. Okay, now if we run this program, so here you can see that L is now updated with minimum length of, which is out of these two, M1 is having a less length, so that is assigned to L. Okay, now we will truncate both M1 and M2 to this length. Okay, so starting with M1, so we will take capital M and assign this one with M1 1 to length. Now copying the same thing and then assigning it to capital M2. Okay, so here what we are doing is truncating both signals with same length. Okay, now again I am running this program. So here you can see M1 and M2 now both are given with same length. Okay, but here the number of rows are greater than, so what we have to do is we have to take one row and columns we have to assign with this value. So what we have to do is we have to transpose the M1 and M2. Okay, so transpose it and right, and then now you can once again run the program. So here you can see, okay, not here, we have to write capital M and this is capital M. Okay, now here you can see the M_1 and M_2 both are given with same length and both are having a same dimensions. Okay, so now this M_1 and M_2 are having these two message signals. Now we'll take another frequency, we'll read this as a 10,000. Okay, and then we'll create one samples NTS and start with it's a 0 and then it has to go with up to this length. Okay, for that one the time duration samplings will be 1 upon Fs. Okay, but if you are going up to this length with this value, it will be it will utilize more memory in our system. So what we can do is we'll divide this L, okay, with 1 upon Fs. Okay, now we'll be assigned, we are creating a samples with this value 6,35,903 samples and starts with a 0. Okay, now we'll execute this. Here you can see so it is giving 904. So what we have to do, we have to subtract this for one sample. So we'll subtract this L minus, because it's starting from 0. Here we have taken 1 to L, so that's why one extra sample as we have generated. Now we can, okay, so with this one we can have, now here you can see that both are of same length. Now we'll generate a new signal x1 cos of 2 into pi nts into fc, and then we generate a multiplexer signal sc, or you can write multiplexer signal ms. Okay, multiplexer signal is equals to m1 plus m underscore 2 into, okay, x1. So this, why we have generated this signal is to like to shift one of the tones to higher frequency. Okay, so now we'll multiply this with this one, right? Now this is a ms signal, it will have both the signals mixed together. Now we'll try to listen this. So or we can first calculate FFT of this one. MSF is equals to FFT of ms, and then we'll try to plot this. I will plot this one. Now you can see that this is the one signal and this is another signal, right? First again we'll check the frequencies components for that one by using this marker. You can put here. So it is showing 4.20 into 10 power 4. If you calculate this, we'll understand that it will be around 3 kilohertz as it is given in our question. So both are 3 kilohertz cutoff. So our frequency is now 3 kilohertz. Okay, so we have to make a use of one low pass filter so that we can remove this signal and we can extract this audio signal. Okay, so now here we'll try to play this sound also. Sound ms comma fs. Here you can see that the both signals have been mixed together, so we have multiplexed. Okay, and both are now mixed and we have generated a new sound. Okay, so we'll stop this here, and now we by seeing that we have already understand that we need one low pass filter. Okay, so now I'm creating a function. Okay, and in this function we'll try to write the program for low pass filters. So I already I've explained how we can write the low pass filter. So I'm copying the same old program. Okay, so in this one we don't need that, and sampling rate is also not required, and from this we'll calculate h value, and we'll try to assign a new name for this one, LPS, and this will need fs. Okay, and so here we have to end the function. So this is the function lps, and we'll call that lps here. Okay, so h is equals to h is equals to lps with fs, and then we'll write extracted signal, extracted tone is equals to convolution of x comma h. So we don't have x here, so x means this ms. Okay, so we'll write ms. Okay, and then we'll try to find out the FFT of this one. So FFT of extracted tone, and then we'll plot this one. Okay, so it is asking for the low pass filter frequency, cutoff frequency. So as we know that our signal is around 3000 kilohertz, so we'll try to give more than 3000 hertz. So we can give 5000 here, and the filter size we are going with 555. So here I have not given the name. And here also I'll give some name. So once again 5000 and 555. Now here you can see this is this plots. From this plot you can understand that two signals have multiplexed together, right? And this is with filter we have able to remove this signal. Okay, now we'll try to play this sound, extracted tone with fs. So we have to give the same numbers. Right, so now you have seen that how we have mixed two signals, and then later how we have extracted them. Okay, so now you take as one more assignment from this one. So what I have done is I have extracted this signal. Now you try to extract this signal by using high pass filters. If you use high pass filter here, okay, if you use high pass filter, then we can remove this one and then we can extract this. But this extracted signal is again, it is DSB signal. That if you have remembered that in our program we have multiplied this one with x1. So x1 is 10 kilohertz. Okay, so 10 kilohertz, and then it's multiplied with m2. So that's why it is shifted. It is shifted to on frequency spectrum. So if you want to employ one high pass filter here, then after high pass filter again you have to do demodulation to extract the that second tone. Okay, I hope this is clear for this one. This is one more application of filters in DSP. Okay, thank you, and we'll meet in next video.